Hi, we're going to talk about chapter 4 now, moving into looking at polynomial functions as well as rational functions. We're going to do section 4.1, polynomial functions and models. After that, we'll skip to 4.5 and then 4.6, so we can talk all about polynomials. Then we'll come back to 4.2, 4.3, 4.4, where we can talk about rational functions also. Okay, I'm going to start with the definition of a polynomial function of degree n. It looks like this. It has a coefficient, a sub n, times x to some power n. Notice the degree n is the same of this is the same as the degree of the polynomial. Then we're going to say, okay, there's going to be another coefficient and x to the n minus 1. So this degree is 1 less than the original. And we're going to add some more terms until we get to a last coefficient times a variable. Notice this x is to the first power. And then we're going to add some constant, right? So, sorry about that. I don't know why that's happening. Where a sub n all the way to a sub 0 are constants. Right? So these subscripts on the a's have nothing to do with their value. They're just counting them. We have to have natural number exponents, meaning that these numbers here are not fractions. There's a 1 here that we don't write. And they're not negatives, so they have to be natural numbers. All right, we're going to look at some polynomial functions. I'm going to switch over to Google, and we're going to look at some polynomial functions of, if I can move the window, hold on just a second. Interesting. Oh, that's interesting. I can't move it. All right, well, maybe I can move the Google. There we go. And we're gonna look at some polynomial functions of different degrees. Okay? So I don't know if you know, but in Google, if you tell it to graph a function, I'm gonna say f of x. You could also use y equals, and I'm gonna put in this polynomial. Minus x, and I'm just going to use the caret key to, to say we're going to go up. Let's see, where is that caret key? Maybe I should have planned this a little bit better. That's interesting, because on my regular keyboard, it has that. Oh, I may need to start this video over again. Let me pause it for a second. All right, here we are, we're back. So I've put in, I want to show you on Google what I typed in. F of x equals minus x squared plus 3x plus 4. And we get this graph here. And let's take a look at that. We notice that it's a parabola, right? And we want to notice that there are two x-intercepts. Right? So there's an x-intercept here at 4, and there's an x-intercept here at -1. And notice I can move this all along here to get lots of points on there. Yeah? These points where, where the graph crosses the x-axis, we call them x-intercepts, or zeros of the polynomial. We're going to start calling them zeros all the time. Okay? So we're going to take a look at that. And then I also want to look at that graph in comparison, in comparison to just the graph of minus x squared. Yeah. So let's enter that. Okay, so if I look at the graph of just minus x squared, I see that I only have one x-intercept right here at 0, 0. Right? But it has the same general shape as the other graph that I just did. All right, we're going to look at a couple more. So let's get rid of the 2. We're going to look at something, a 4th degree polynomial, and it's going to be one that does not have a minus up front. So we're going to do x to the 4th minus 3x cubed, 3x, uh-oh, now I don't know how to do the cube. I did a copy paste. Alright, I'm going to pause again. Okay, I've got the graph of x to the 4th minus 3x cubed minus 4x squared. So take a look at this, and we'll think about our x and y, our x-intercepts or our zeros. So it looks like I have one around at 4, and we also have one here at 0, 0. Okay, so take a look at the general shape of this, and notice that its first term is x to the 4th. Now what we're going to do is I'm going to draw a comparison to just the graph of x to the 4th power. Notice that it has the same general shape. It has a little bit of, a little fewer bumps along the way. Yeah, and we're also noticing while we graph these things that at zeros we can either cross the x-axis or we might just touch the x-axis, right? It might just be a place where we touch and go on. All right, so now I'm going to attempt to put in x to the 6th minus 3x, and I've decided that I can, 3x to the 5th minus 8x x to the 4th plus 18 x to the 3rd power. The good thing is if you're taking notes, and I'm going kind of slowly so you can write it all down, 25 plus 25x squared minus 15x, and minus 18. And let's graph that. I'm going to move this up just a tiny bit. Well, I guess we don't need to. Now take a look at this guy, okay? Now notice it comes down and we have 4 zeros. 1, 2, 3, 4. A couple of zeros we cross the x-axis here and here, and a couple we just touch, like right here at -1 and right here at 3. All right? But I want you also to notice that the graph is coming, it's going up. As x gets smaller and smaller, the y is going up to positive infinity, and as x gets larger and larger, it's also going up to positive infinity. And let's compare this to the graph of x to the 6th. Just the graph of x to the 6th. And we look at it and we say, oh, it has the same kind of thing happening here at the end of these graphs, right? So all of these graphs, they have even exponents as their degree, as the first degree, the nth degree, and all of them ends go in the same direction. So we're going to say that if n is even, as x goes to infinity, so as values of x get larger and larger, y goes to infinity, and as x goes to negative infinity, y also goes to infinity. Or, as x goes to infinity, y goes to negative infinity, and as x goes to negative infinity, y also goes to negative infinity. And so you might be saying, what is all of this stuff? Well, basically, I'm just saying that if you have an even degree of your function, the ends of your function are going to point in the same direction, either both up or both down. And of course, here in the middle, there's all kinds of wiggles. Things might go up and down and cross the x-axis a couple more times, or they may not. That's true for even functions, even degree polynomial functions. Okay. Now let's check out some odd degree polynomial functions and see what happens there. Okay, so we're going to go back to here and let's put in some odd degree functions. So first of all, how about a line? 3x plus 2, right? We all should know what that's going to end up looking like. Okay, so notice it crosses the x-axis one time, and its ends are going opposite directions. All right. And let's take a look then at another odd degree function. We'll say x cubed minus 3x squared minus 3x squared minus 6x plus 8 minus 6x plus 8. And let's graph that. All right. So notice, again, this is a third degree function. It's crossing 3 times, 1, 2, 3, and its ends are pointing in opposite directions. I'm going to compare this to just the graph of x cubed and see what it looks like at the ends. Notice it's generally still shaped in the same way as the function that we just looked at. There's less going on here in the middle. It's a little bit smoother. All right? And let's consider one more. We're actually going to say minus x. We're going to look at a fifth degree function, still an odd degree, plus 3x to the fourth plus 6x cubed plus 6x, x cubed minus 8x squared minus 8x squared. And let's graph that. Okay, and we see, oh look, there's a minus out front. Our ends are still pointing in opposite directions, but notice it's different than when we had a positive leading coefficient here. Again, we're crossing, a couple of times, 1, 0, -2, 4. These look like our x-intercepts. And let's compare that to the graph of just minus x to the fifth. Just minus x to the fifth. Notice it has the same general shape, a few less wiggles happening here. So, all three of these polynomials, their ends go opposite directions. So earlier we said that if n is even, the degree of our polynomial is an even number, then the ends point in the same direction. Well, now we can say if n is odd, we can say as x goes to infinity, so as x gets bigger and bigger, y goes to infinity, and as x goes to negative infinity, y goes to negative infinity. So we're saying as x gets smaller and smaller and smaller, y gets smaller and smaller. So our graph looks something like this, except that, again, there can be wiggles happening in there. Or it might face the other way. As x goes to infinity, y goes to negative infinity, and as x goes to negative infinity, y goes to positive infinity. So the idea is that the ends are pointing in either direction, in opposite directions. Okay? In all cases, we call this end behavior. End behavior. Right? What is happening at the ends of the function? What are they approaching? Are they getting bigger and bigger and bigger in a y as a y value as x changes? As x gets bigger or x gets smaller, what's happening? Okay? In all cases, end behavior always matches that of the power function and we can talk about a power function as a sub n x to the n. Basically, it just has one term raised to that degree with the same degree of whatever polynomial we're looking at. So if it starts with an x to the fifth term, no matter how many terms it has after that, it's going to behave at the ends like x to the fifth. Okay,